Hello and welcome to the first lectureclips.com tutorial on kinematics and kinetics. This is again an introduction video, so we will not solve any specific problems today, but just have a look at what is kinematics and which basic quantities do we need to describe kinematic processes. So kinematics is another branch of classical mechanics, like statics for example, but with a big difference that the systems in kinematics are not in equilibrium and staying still, but in kinematics it's all about the motion of a point or body in space. The difference between kinematics and kinetics is that in kinematics we do not ask about the cause of the motion, and in kinetics we do. This means that in kinematics we will not consider any forces or torques, okay? We just know that the body has a certain velocity or acceleration, for example, but we do not ask for the reason. And in kinetics we say, well, this body has a velocity, but just because the force F is acting on it, or the torque M for example. So we will work with forces and moments again in kinetics. First we will have a look at kinematics, such as in this clip, and later on we will continue with kinetics. And this is because the formulas and expressions from kinematics are also valid in kinetics. But the other way around, it does not make sense, because we cannot use formulas of kinetics that contain forces and moments and then use them in kinematics, because there are no forces and moments at all. Okay? When talking about kinematics, we immediately have to differentiate about absolute kinematics and relative kinematics. We will start with absolute kinematics because, once again, the formulas of the absolute kinematics are also valid in relative kinematics. But the other way around, it does not make sense again. Okay? Just to give a little structure at first. Okay, now, the basic quantities that occur in kinematics are the position, the velocity and the acceleration. And these three quantities are vector quantities, okay? So we will depict them as a vector arrow. This means that they are signed. So we will work again with coordinate systems. For example, a velocity vector will have a positive or negative sign depending in which direction it points. Let's have a look at the velocity first. Before we start, I just want to mention the difference between velocity and speed. So as I said already, when talking about the term velocity, we're talking about a vector. Now, if we don't care about the direction or sign of the velocity, we say speed. So the absolute value, the magnitude of the velocity, is called speed. Now, velocity is nothing else than the change of the positioning coordinate. I want to show you what I mean using this draft here. When talking about velocity, it is always necessary to mention related to what the velocity is measured. This is very, very important, and also the reason why we have to differ between absolute and relative velocity. Okay? If I don't mention related to what I'm measuring the velocity, it does not even exist. Now let's assume that this car here has a speed of v1 equals 20 miles per hour, and this one here has a speed of v2 equals 30 miles per hour. So this car is basically taking over that one here. And this is an observer on the roadside which is standing still and is not moving. Now, if I say that the car 1 has a speed of 20 miles per hour, I mean 20 miles per hour related to this observer here. Or related to some fixed point on the roadside or the road itself. And if I say that this car here has a speed of 30 miles per hour, I again mean 30 miles per hour measured related to this observer here. If I now ask, what is the speed of this car related to that one here, I get a completely different value. Because it is not 30 miles per hour anymore, but the difference of these speeds here, which is 10 miles per hour. Now you see, if I don't mention related to what I'm measuring the speed of car 2, for example, it does not make sense to mention the speed at all. I actually cannot talk about speed in that case, okay? If there is no observer, no road, no car 1, nothing at all, okay? But just the car 2, I have no idea how fast it is going. And this is why it is so important to mention the reference frame to which I relate my velocity on. Okay, the important thing is that the velocity that is related to the fixed observer is called absolute velocity, and the velocity from car 2 related to car 1 is called relative velocity. Now, the observer or any fixed point would be a so-called inertial frame of reference. This is basically a frame of reference, so a coordinate system, which is not moving, fixed with our Earth, and in which Newton's first law is valid. Let's have a look at a position. How do we describe a position? Okay. Now, this is a general coordinate system, not moving, let's assume. And this is the point of origin, and here you can see the point P. Now we can set up the positioning vector, which is the connection from 0 to P. I just called it RP. You can see it here. Just a few words about the notation. Our vector RP can be displayed as the connection from 0 to P, which would be RP0. Okay? So the first point is the point to which I go, and the second one is the point from which I come. Now, if point P is moving, then the vector RP is not constant anymore, but depending from time. So it's RP of t. Because the more time passes, the bigger or smaller RP will be. And in that case, I can derive the positioning vector with respect to time, and I get the velocity Vp of point P. Again, a word to the notation. Since we don't want to write down the differential d over dt every time, we can simply make a dot over the quantity. Yeah? And for the second derivative, it would be 2 dots, for example. So the dot tells us that this is a derivative with respect to time. With a prime mark, it would be a derivative with respect to position, like we had at the deflection curves in the statics clips. And the acceleration is nothing else than the derivative with respect to time of the velocity, or the second one of the positioning vector Rp, so Rp dot dot. And this is how we obtain a velocity and acceleration in general. This means that we can use these expressions every time if a velocity or acceleration is rectilinear. Just in special cases we can use them if they are rotational. And now let's have a closer look on this. Well, this is how we describe rotational movements. First I will explain the draft to you. Here you can see the point P, and this point is only able to move around this circle here. Here's the coordinate system, which is fixed, so this is an inertial frame of reference, x, y and z direction. Now at a certain moment we are looking at point P, the positioning vector r is tilted by the angle phi. And now if P moves around this circle, the angle phi will change as well. Phi will change by time, so this angle is a function depending from time. This is phi of t. What we want to know is the absolute velocity of P, so Vp related to this inertial frame of reference. Now in the first step we have to build up the positioning vector Rp here, and we have to do this in this coordinate system. So it is r times sine phi minus r times cosine phi and 0. Because we can put a right angle triangle over here. This side would be r times sine phi, this is the x direction, and this would be minus r times cosine phi because we have to go in the negative y direction. And now we can already see that the vector Rp is depending from time as well, and this is because of the angle phi. Now, before deriving Rp with respect to time, we have to define a new quantity though, which is called the angular velocity. The angular velocity is also a vector, and it is defined by the change of the angle by time. So actually nothing else than the first derivative of the angle phi. Like the normal velocity was the first derivative of the distance, of the position, the angular velocity is the first derivative of the angle. It basically tells us how fast something is spinning. And equivalent to the normal acceleration, the angular acceleration is the second derivative of an angle, or the first derivative of the angular velocity. The common notation for the angular velocity is this small omega here. Now, the angular velocity has a very special property, and you really need to remember this. The vector of the angular velocity, omega, is always perpendicular to the plane of rotation. In our case, point P is rotating in the xy plane, what you can also see here, because the z component of Rp equals 0. So we already know that the angular velocity omega has to be perpendicular to this plane. And in that case, it means that omega is pointing in the z direction. Of course, omega could also be negative. For the sine, we have to think back to the right-hand rule. Here, phi is growing counterclockwise, and if we simulate that movement with our right hand, the thumb points into the same direction as the z-axis, so it's positive. If P would rotate the other direction, the thumb of our right hand would point downwards against the positive direction of the z-axis, and omega would be negative. Okay, we have two possibilities to find the absolute velocity of P Vp. But the first one just works because this is an inertial frame of reference and Rp is depending from time. Just because Rp is already displayed in this coordinate system, in the coordinate system related to which we want to find our velocity, we can simply derive Rp with respect to time. So then we get our absolute velocity Vp. We can simply do this by deriving the components separately, and we get this expression here. Please pay attention to the mathematical aspect here because of the chain rule. Actually, here we have sine of phi of t, and we are deriving with respect to time. So the sine turns into the cosine, and then we have to multiply by the derivative of phi, which, as we already know, is phi dot, the angular velocity. R is just a constant and stays in front. And the derivative of cosine is minus sine, so here we get a plus at the end, and then again we have to multiply by the angular velocity phi dot. Please always be aware of the chain rule. This happens very often in kinematics and kinetics, that we derive with respect to time. One of the most common mistakes that students do is to forget to use the chain rule. The second possibility is to use the expression for a rotational velocity. We notice that p just moves around a circle, so it is a rotation, and in that case we can use the expression for a rotational velocity, which is Vp equals omega cross Rp. Every time we want to find the velocity of a point that rotates, we can use this cross product. In our case, Rp is just the radius r. Please make sure that you are really comfortable calculating a cross product, since it often occurs in kinematics. And here you can see already that for this possibility we already need the knowledge that omega is pointing in z direction and is positive, because otherwise we would not be able to build this vector here. And the cross product gives us exactly the same result as above, as you can see. Now I have another example for you. In the second example we have the exactly same point P and the same circle here, and once again P is only able to move around this circle here. But this time our coordinate system is not fixed but rotating. This is the very big difference to the case before. This is not an inertial frame of reference. This system is moving with P. And according to Isaac Newton, every system that is moving with constant rectilinear velocity is also an inertial frame of reference. But not a rotating one. Not this one here. This is not an inertial frame of reference. But we still want to find the absolute velocity of P. So the velocity of P related to an inertial frame of reference, not related to this system here. In kinematics we often use a rotating coordinate system if we want to describe rotational movements, because the description, the calculations are a little easier. So, because of the fact that the whole system is rotating with the angular velocity omega, the system is rotating with the angular velocity omega, the vector Rp is just r in x direction, just the radius. Because the x-axis will always point towards p, because they both rotate with omega. And this will not change by time. This time we cannot just derive Rp to find the absolute velocity of p, because Rp is constant and not depending from time, as you can see. The following is very important for the understanding of the difference between absolute and relative velocity. As I said, Rp is constant this time. So if we derive a constant with respect to time, it will give us 0 as a result. But the absolute velocity of p is not 0. Let's imagine together that point P is able to move in the direction of the radius, so towards the origin point, let's say. In that case, Rp would depend from time, since it would be a rectilinear movement, and we could get a result if we derive Rp. But this would not be the absolute velocity of P. This would be the relative velocity of P related to this rotating coordinate system. Okay? But in our case, Rp is constant and we're looking for the absolute velocity. Imagine that somewhere here there is an inertial frame of reference. Even though it is not drawn anywhere, it is there, somewhere here, just fixed. And we want to find the velocity of P related to this inertial frame of reference. And to find the absolute velocity, we can use the expression with the cross product again. Just deriving the vector rp does not work in that case, because it would be the relative velocity of p related to this system, which is 0. But with the second possibility it works. This is the expression for a rotational velocity. And we get this result, r times phi dot in the y direction. A very, very important property of a rotational velocity, like Vp, is that it is always at right angles to the radius. It is perpendicular to the radius. This is why it is also called the tangential velocity. And here you can see that the descriptions are much easier here, since we don't need the trigonometric functions cosine and sine. This is why we often use rotating systems in kinematics if we want to describe a rotational movement, because the description is easier, as I said before. At the end I will tell you another very, very important kinematic connection. This is the last one for today, I promise. Actually there are no more important formulas if we are finished with that one. Just the acceleration of a rotational movement, which I will explain in another clip. Okay, again we have a general coordinate system here not moving. Here is the point P1 and here is the point P2. Now in many cases the velocity of the point P2 is asked, but we do not know this distance here. We do not know rp2, because otherwise we could simply derive it with respect to time. But we do not know it. But instead we do know the velocity of point P1, so Vp1. And we also know the connection from P1 to P2, so rp to P1. Now it is not surprising that we can build up the vector rp out of these twos here. So rp2 equals rp1 plus rp2p1. This is just a simple vector addition. And now if we derive the whole equation with respect to time, we get the important connection Vp2 equals Vp1 plus Vp2p1. Okay. So the velocity of point P2 equals the velocity of the point P1 plus the velocity of P2 related to P1. And now we think a little forward, and then we know that if point P2 moves rectilinear from P1, or for example rp2p1 is depending from time, Vp2p1 would be simply the derivative of rp2p1. And if point P1 is moving and P2 is rotating around P1, then in that case Vp2p1 would be omega cross rp2p1. Of course, this connection is also valid for the acceleration. So ap2 equals ap1 plus ap2p1. This is it for this time. I hope that I could help you understand the basics of absolute kinematic a little better. It might be a lot of new information for you, but you will see that with a little practice you will understand it more and more. Just watch the next few clips. See you next time.